So hello smarties again and welcome to my channel. So in here we're going to start off with looking at some various properties of elements or atoms in a particular compound. One important thing you need to note is the concept of electronegativity and bond polarity. So 1.7 we go, or let's say 1.6 for now, hopefully I'm right. So we're going to look at electronegativity and bond polarity. So these two concepts are quite important and sometimes they're quite interchangeably in terms of when you're supposed to use this particular concept. So sometimes if you're looking at equal sharing of electrons between atoms, that leads to a concept known as non-bonding of covalent bond, because covalent bond involves sharing, but then there are two cases of covalent bonding. You either have equal sharing or unequal sharing. So the equal sharing of electrons will always lead to non-bonding, and a typical example will lead to non-polar covalent bond. And a typical example of this is hydrogen gas. So it means that the electrons will be somewhere in the middle between the two bonds, or between the two atoms, sorry. And on the other side we have ethylene, and ethylene specifically we'll be looking at the carbon-carbon bond. So this carbon-carbon bond here, they are quite equal in the sharing of the electrons, or I would say the bond electrons over here. And on the other side, we now have a case where we have unequal sharing of electrons. Now the unequal sharing of electrons is called polar covalent bonding. And a typical example of this is chloromethane. And chloromethane, which has carbon and hydrogen bonding around it, also includes the presence of a chlorine bond in with the carbon over here. So if we look much closer, what we see here is actually there's a pool of electrons towards the chlorine atom, where there's less electron density in the carbon region, but a high electron density around the chlorine atom. So this will lead to a form of a dipole moment, which is positioned in the carbon area, and while on the other side we have a negative dipole in this particular case over here. So this dipole separation over here, we tend to include the concept by introducing an arrow where the head is pointing towards the chlorine, which shows that there is a higher electron density towards the chlorine, and chlorine is more electron rich compared to this other region where carbon is positioned over here. So this particular arrow shows the bond polarity, and it's kind of a symbol also. And this bond polarity has a unique abbreviation, which is U or mu. So where mu is known as the dipole moment. So this dipole moment over here looks at the amount of charge that is present in this particular bond, either being a positive charge or a negative charge or a partial charge over here. So once you're able to multiply this charge by the distance between these two atoms, or the bond distance between the two atoms, then you can know the level of the dipole moment you have in this particular molecule over here. So the calculation is mostly represented as mu equals to the dipole moment, by the, I would say, the amount of charge separation between the positive and negative charge multiplied by the distance between the two atoms over here. So the tools that are mostly used in measuring this particular degree of polarity can be the EMP, which means the electrostatic potential mapping. So this kind of mapping uses the concept of colors and various colors to illustrate the degree of or the distribution of charges within a particular molecule. So these colors ranges from the visible light spectrum, where red is a region where you have the highest electron density position, to purple, which has a very low electron density. However, we have intermediate regions where green, yellow, or orange could signify intermediate in terms of the electron density overall. And therefore, an example of this case would be chloromethane. So let me just put the oxygen or hydrogen, and you have carbon over here, hydrogen, and the hydrogen bond over here. So I'll just shade here to be carbon also, and this part here we have a big atom which signifies chlorine. I'll just put dots here to signify chlorine over here. So this mapping is in this some kind of nature over here. So in this case here we have this region which is purple to blue, then there is this region over here, purple to blue, then this region over here I would say is between green to yellow to orange, and while this region over here is red. So red is the part where you have the partial negative charge, which is where the chlorine is positioned, and while this region here, which is the purple to the blue, is actually the partial positive charge region over there. So that is one way of looking at it. On the other hand, we have a much more handy tool, and this handy tool is electronegativity. So electronegativity just gives you a particular numerical values which explains which positions is much more electronegative compared to the other one. So if you know from the periodic table, we know that electronegativity increases from left to right across a period overall. So this also helps in being able to predict polarity of bonds, and also gives the direction of the dipole moment, which is this particular arrow over here. So in this particular case now, we have a particular scale which we mostly used to actually determine this particular concept properly. One of these scale is the Pauling electronegativity scale, and this scale enables us to predict the polarity of covalent bond. And what we know is that the higher the electronegative element we have a stronger attraction of the bonding electrons towards that particular element overall, and therefore making that element to have an electronegative partial charge overall. So if you look at the periodic table, the most important thing you need to note is that Nitrogen, oxygen, and all the halogens in the periodic table, they all have a higher electronegativity value than carbon. However, we have elements like sodium, lithium, and magnesium which have a lower electronegativity than carbon, and sometimes we usually consider the bonding between carbon and hydrogen to be a nonpolar bond in most cases because they both have a really close electronegativity values. Overall, thanks again for watching this, and hope you understand this concept, and this is going to be handy when you're looking at interaction within atoms and molecules overall. Thanks for watching. Please don't forget to hit the like button, share, and subscribe. Have a good day, guys. Peace. Love you all. Bye, and be smart.